Hi there. Today we're going to be looking at Fermat's theorem of stationary points. We're going to first be looking at the formal definition of Fermat's theorem, then going to some intuitive understanding of what the theorem actually says, and finally we're going to conclude by looking at a proof that proves Fermat's theorem. The formal definition of Fermat's theorem says that if a function f is defined from reals to reals and is differentiable at a real number c, and if f has a local maximum or minimum at this point c, then the derivative of f at the point c is equal to 0. Let's get an intuitive understanding for exactly what Fermat's theorem is saying. I'm going to draw a random graph f, and there will be a local maximum at a point called c. If we look at the left-hand side of the function, at the x values close to c, we'll see that the function is increasing, which means that the gradient must be positive, and that if I were to take the derivative of any points along this segment, they must be greater than 0. If we look on the right-hand side of the function, just after the point c, we'll see that the function is decreasing, which means that the gradient must be negative, and if I were to take the derivative of any point along this segment, it must be less than 0. Because this function is continuous, and it started increasing at one point and then began to decrease afterwards, it makes intuitive sense to say that at some point the derivative of the function must have equaled 0. This will be at the point where the function changes from an increasing function to a decreasing function, and therefore this must have occurred at our local maximum, which is the highest point in our local region that our function can meet. Next, we're going to be doing a quick recap of derivatives by first principles. I imagine that you already have a good understanding of this topic already. However, the thinking behind first principles can be very helpful for when we try to tackle a proof of Fermat's theorem. So we have a function f, and we are looking for the gradient at point x. When we try to sub this into the gradient formula, we run into an issue because we need a secondary point to be able to determine the gradient of a section on this function. So we look for a point close to x, which we will call x plus h, where h represents the distance between the x values of these 2 points. What we see is that the gradient is pretty close to that which we are looking for the gradient at x. And so we plot a point closer, and we try to get the gradient of that, and closer and closer. And each time we get closer to the gradient we are looking for. And this leads to the formula for deriving by first principles, which says that the derivative of the function at x is equal to the limit as h tends towards 0 of f of x plus h minus f of x over h. We can now move on to our proof of Fermat's theorem. Our first step is that we define a function f, which is defined from reals to reals, that is differentiable at c, and has a local maximum at c. This is very similar to the intuitive example I had at the beginning of the video, so I'll be putting that intuitive example here to explain throughout the proof how we can derive all of these steps. Our second step is to note that because we have a local maximum at c, for all the x values that approach c, f of x minus f of c will be smaller than or equal to 0. And intuitively this makes sense. We have a local maximum at c, so there is no y value that could be greater than the y value at c. Our third step is to note that for x values near but smaller than c, c minus x must be smaller than 0. Therefore, we can say that f of c minus f of x over c minus x is greater than or equal to 0. If we have a look at the two inequalities, with both of them either being negative or equal to 0, it intuitively makes sense that we can write an equation like this. We can then take the limit as x tends towards c from the negative side on both sides of our equation. The limit of a constant such as 0 equals 0, so on the right hand side we still have 0, and on our left hand side we have a very familiar looking equation which, other than the fact that it's a one-sided equation, is essentially a derivative by first principles. Just as we did in step 3, we can say that for x near c but greater than c, x minus c is greater than or equal to 0. And just like before, if we take the fraction of these two inequalities, f of x minus f of c over x minus c must be smaller than or equal to 0. We can then combine these two one-sided limit inequalities that we have to find that 0 must be smaller than or equal to the derivative of point c by first principles, which is smaller than or equal to 0. And therefore the logical conclusion is that the derivative at point c must be equal to 0. You can continue your proof to prove that at a minimum point this will also hold true, but generally you can stop your point here and say that in a similar fashion we can prove that at a minimum value of a function, the derivative at c, which in this case would be a minimum, must also equal 0, and therefore Fermat's theorem holds. I hope you have enjoyed this video and have learned more about Fermat's theorem, the understanding behind it, and how we might prove this theorem, and I will see you in another video soon.